Welcome to Enlightenment Land, starring Tim. So some of you might be wondering, what is light? Well, here in Enlightenment Land, we are here to tell you. Light acts like particles traveling in straight lines, but if you change the circumstances, it can behave like sound waves or water waves. And if you change them again, light behaves neither wave-like nor particle-like, but has properties of both. There are three different models of light: wave, ray, and photon. The ray model utilizes telescopes, and the photon model is reliant on quantum physics. Today, as we go through Tim's journey, we will explore the properties of light waves and the central idea of wave optics. So, propagation of light waves. Since light consists of rays that travel in straight paths, light passing through an opening makes a sharp-edged shadow. Additionally, light waves oscillate so rapidly, some at the frequency of 10 to the 14th hertz. We cannot directly observe the crest and the troughs of its electric or mechanical fields, so today Tim is going to explore the properties of waves through water. After passing through an opening, waves spread out to fill the space behind the opening. This is called diffraction. In this image, a wave is approaching the opening from the top and the wave is spreading out behind it. These waves do not travel in a straight line because they bend if the size of the object is not comparable to the size of the wave. But if a water wave is passing through an opening that is many wavelengths wide, the wave coming in moves more straightforward. We find that a typical wavelength is only about 0.5 nanometers. So Tim accidentally finds himself in a portal and ends up in space, or also known as the Great Vacuum. In the vacuum, he finds a light wave. Light waves are able to travel in space because it is a self-sustaining oscillation in the electromagnetic field. Light is an electromagnetic wave and does not require a material medium to travel. All electromagnetic waves, including light waves, travel in a vacuum at the same speed, the speed of light, 3 times 10 to the 8th. The wavelengths of light are extremely small and range from about 400 nanometers for violet light and 700 nanometers for red light. Waves outside of this range are not visible to the human eye. Prisms are able to spread different wavelengths apart. White light is all the colors wavelengths combined. The spread of these colors through a prism is called the visible spectrum. Wavelengths and oscillation frequencies have an indirect relationship. If the wavelength of a light is small, then its oscillation frequency is high. Frequencies of light waves are about 1,000,000,000,000, 10 to the 12th higher than sound frequencies. Light waves slow down when they pass through transparent materials like water and glass because of interaction between electromagnetic field of the wave and electrons in the material. Index of refraction, n, is the speed of light in a vacuum divided by the speed of light in a material. It is always greater than 1 because speed in a material is always less than in a vacuum. If the speed of light changes as it enters through a transparent material such as glass, what happens to the light's frequency and wavelength? Because V equals lambda f, either f or lambda has to change. The frequency of a wave does not change as the wave moves from one medium to another. For example, think of a sound wave as it impinges on the surface of a pool water in the air oscillates back and forth. This frequency is the same as in air as it is in water, and the same is true for electromagnetic waves. This picture shows light passing through a transparent material. Notice that the frequency does not change, therefore the wavelength must change. A multi-slit device is called a diffraction grating. The drawing shows a diffraction grating. The slits are equally spaced at a distance d. This is the top view of the grating. The wave emerging from each split is in phase with the wave emerging from every other slit. Each of these waves spread out just like the light wave, and after a short distance, they all overlap with each other. This next image shows a zoomed out version. It shows that n light waves from n different slits will all be in phase with each other when they arrive at a point on the screen at angle theta, such that d sine theta equals m lambda, and m can take all values 0, 1, 2, 3, etc. The screen will have a bright constructive interference fringes at the values of theta m, and we can say that light is diffracted at the angle theta m. The position of the bright fringes due to diffraction grating distance L from the screen can be determined through the equation y equals L tan theta. This next image shows the intensity on the screen due to 3 diffraction gratings. As the number of slits increases, the fringes gets narrower and brighter. The science of measuring wavelengths of the atomic and molecular emissions is called spectroscopy. Each wavelength will diffract at a slightly different angle, and if n is large, we can see 2 distinct fringes. Using 2 different colors of wavelengths, we can illustrate this. The 2 wavelengths have been separated. The blue light has a longer wavelength than violet does, and it diffracts more. All wavelengths overlap at y equals 0. Light bounces like crazy. This mirror, with many grooves, which are reflective stripes, when illuminated, becomes the source of a spreading wave. Thus, an incident light wave is divided into n overlapped waves. It is the same as an interference pattern of light transmitted through n parallel slits, and such wavelengths go at different angles. This is the same concept with a DVD. The microscopic dents on the DVD act as diffraction gratings, and so the rainbow of colors seen on its surface display interference. Now let's discuss thin film interference, which is the interference of light waves when reflected from two boundaries of a thin film. In this candle picture, a light wave encountering a piece of glass is partly transmitted and partly reflected. Light is partially reflected not only from the front but as the back as well, and it exits the glass as the air. This leads to two reflections seen in the glass by the candle. In this next picture, when the light wave moves from a medium with higher speed of light, with lower index of refraction, to lower speed of light, the reflected wave is inverted, also known as a phase change. The light wave undergoes a phase change if it reflects from a boundary at which the index of refraction increases. In this next picture, the incident wave is transmitted through a thin film glass, and part of the incident wave reflects from the first surface. Then part of the transmitted wave reflects from the second surface. Finally, the two reflected waves overlap and interfere. Two major formulas that Tim learns through his experience in Enlightenment Land include 2t equals m lambda over n and 2t equals m plus 1/2 times lambda over n, where m equals 0, 1, and 2. These are the basic principles of single-slit diffraction. Now, a major innovator and scientist of this experiment includes Huyen and his principles. His first principle is regarding plane waves, and in which each point on a wave front is the source of a spherical wavelet that spreads out at that wave. His second principle, at a later time, shows that the shape of the wave front is a curve that is tangent to all the wavelengths. Now let's discuss the double slit experiment. It was first performed by Thomas Young in 1803 when he presented his findings to the Royal Society of London. By asserting that light has both the properties of a wave as well as a particle, he helped lay the foundation for what is known as today as quantum mechanics. This experiment is one of the most duplicated in all of physics, and it is considered by many to be the most elegant. Today, in Tim's experience through Enlightenment Land, he performs the double slit experiment using Young's basic principles. In its most basic form, the double slit experiment consists of a directing of a beam of light through a pinhole, then through two slits in a sheet of opaque paper, then finally projecting the beam onto a screen of some sort. During the time, there were no forms of non-natural light, and so what he did was, looking through a plate of looking glass, finally split in the two by a horizontally held card. When dealing with properties of light, we say that it is interfered constructively, which means that the one crest of the wave meets a crest of another wave. And the basic principle learned is that light is split, and through two different slits, light can be shown and different wavelengths will be recorded. Now, after a long day of Tim's journey through Enlightenment Land, we hope that Tim and his fellow classmates learned a lot about wave optics and its basic ideas.